Let's talk about this interesting subject of finding the probability of p. Right? We spoke about Bernoulli distribution, and we said it has two outcomes, which we often denote with 0 and 1, and the probability of p of encountering the outcome 1. Hence, the probability of an outcome 0 should be 1 minus p, so that they add up to 1, right? The total adds up to 1. Good, but where are we going to get this p? Right, so in some cases, it's very easy. So for instance, if we're dealing with a coin, fair coin, right, it's very reasonable to assume that p is going to be 50%. So 50% of a chance of encountering heads, 50% of a chance of encountering tails. But that's not always as easy as with coins when we're using Bernoulli distribution to some other phenomena. So let's say I spoke about maybe getting infected with disease, right? So where do you get this p? Is there an easy way to just assume what is p? And it may not be the case. And even with the coins, it's actually interesting. We just said, well, it's 50%, well, based on some symmetry, or a coin looks like fair, like why not? Why shouldn't it be 50%, right? So we would assume that. But if you try to calculate the probability of heads or tails based on physics, maybe inserting the physical measurements of the coin and other things, it'll be actually quite tricky. It won't be easy. It will be very difficult actually to estimate p and then test it whether it's exactly 50%. Right, so the point is the following, that when we're applying Bernoulli distribution to actual business or economics problems, it may not be easy to find out a good p by just like looking, analyzing the phenomenon itself starting from initial principles. So in that case, what are we going to do with p? How are we going to find it? So one way to do it would be using statistical approaches. And how would we proceed, right? So a reasonable approach seems to be, or quite intuitive, is to get let's say a coin. If we're talking about the coin, we will toss it n times, and then we'll observe how many times there were heads, and divide it by n, and that will probably be a good estimate of this probability. So in case of a coin, if it wasn't a coin, if it was some natural or economic, maybe social phenomena, then the idea would be to observe that phenomenon maybe n times, observe how many times you got the desired outcome, and then divide it by n, and maybe that will be a reasonable estimate of the probability. So in statistics, as you probably remember, we use a hat symbol to denote the estimated quantity. So p here would be a true probability of this Bernoulli distribution if we knew it, but it happens so in this case I'm assuming we don't know it and we're trying to estimate it statistically. So how are we going to do it? Well, I'm going to get, with coins, I'm going to get 10 coins, and I'm going to just toss them and see how many heads I'm going to get. Okay, this was heads. So let's count, right? 1, 2, 3, 4, 5, 6, right? So we got 6 heads, and we got 4 tails. So I'm going to write it down as follows. Just ignore it, right? So my first sample was 6 out of 10. Let's try it once more, right? Or maybe a couple of times more. We'll do the same thing. We'll take the same 10 coins, and I'm going to toss them. All right, let's see what's going on here. 1, 2, 3, 4, 5. Ooh, 6 again. Interesting, right? 1, 2, 3, 6, 4 heads. Sorry, 4 tails. All right, so our table looks like this, right? We have 2 observations, 6 and 6 each. Let's try a couple of times more. Okay, what's going on here? Are they rigged? 1, 2, 3, 4, 5, 6, 7, 8. You see, we have 8 heads and 2 tails. This is how our table looks like now. Okay, and one final time. One, 2, 3, 4, 5, 6 again. Interesting. Right, 6 heads. So what have we learned so far from this little experiment? What we have learned is the following. So for a minute, just ignore the other again, but let's just look at the first sample. Right, we got 10 coins and we got 6 heads out of 10 coins. And then we had another observation where we got 6 and then 8 and then 6 and so on. So what we're learning here is the following, is that our estimate of a probability, the estimate of probability is the random number itself. This estimate is a random number itself, and that random number will depend on a sample. So any given sample, so in the first sample we got 6, in the second we got 6, in the third we got 8, and so on. In any given sample you can have a random number of heads showing up. That is very important, right? And the other thing which we have learned is that this number is quite far from 5, which we are expecting. We're expecting that there should be 5 heads in average, and in our case the average is more like 6 point, let's say more like 6.75 or something like that, right? So it's quite far from 5. Why is it so? Well, because the sample is very small. We could imagine that if instead of tossing 10 coins we tossed maybe 1,000,000, then maybe the estimate of the probability would have been much closer to 50%. Right? So it's important to have a large sample size to decrease the variation of the variability of your probability estimate, right? P hat. And that's one thing, but the other thing is, as I said, the main thing is that our P estimate itself is a random number, 0.6, 0.6, 0.8, 0.6, and so on. And it has its own distribution, right? So when we are estimating the probability of which corresponds to the Bernoulli distribution, right? We're observing some phenomenon and then we're trying to estimate the probability. We'll end up with this probability itself having its own distribution, maybe, right? So this is a random number itself. Every time we get a new sample, right, with every sample we will get a different estimate of the probability of Bernoulli distribution, and that's a very important observation, because it brings up to the notion of the sample distribution of an estimate. Right? But I showed you one way of estimating the probability of Bernoulli distribution through observing your phenomena and then applying some statistical technique, which in this case turned out to be a very simple ratio of observed heads over the total size of the sample.